This is the first lesson in trigonometry unit. We'll talk about angles and arcs. What's an angle? Well, an angle is a space between two rays. For example, if I have a ray coming from this point called a vertex this way and the other ray that way, that the angle is actually the whole space of the plane contained by these two rays. The first ray will be called initial and the second ray will be called terminal side of an angle, and the angle opens from the first to the second, so the direction of opening is important. If the angle opens or rotates counterclockwise, then we assign a positive measurement to such an angle, and for clockwise rotation we assign negative measurement. So we have these two possible situations. Either a positive angle, which means the rotation is counterclockwise from initial to terminal side, or negative angle, rotation is clockwise. So CA will be initial ray and CB will be terminal ray. We can measure angles by using degrees. 1 degree is a measure of 1/360th part of a complete revolution. So if we have a complete revolution from 0 to 360 and we divide this circle into 360 equal parts, then one such part will have a measure of 1 degree. Therefore, 360 degrees corresponds to complete revolution. And to measure more precisely than that, we can cut the degrees into 60 minutes. We'll record this using a mark in the top. And 1 minute can be cut into 60 seconds. So this system works the same way as hours, minutes, and seconds. But this time is degrees, minutes, and seconds. Let's recall some names of special angles. For example, two angles that add up to 90 degrees are called complementary angles. So those are angles that add up to 90 degrees. For example, this angle and that angle. Angles that add up to 180 are called supplementary angles. Those are angles on a line. And it could be two angles or more. For example, these three angles are called supplementary because when added, they create 180 degrees. An angle is said to be in standard position if we place it in a system of coordinates in such a way that initial side corresponds to the positive part of x-axis, the vertex is at the origin, and the terminal side opens counterclockwise for a positive angle. So that's standard position. We're going to refer to it in subsequent lessons. If we have system of coordinates, it cuts the plane into 4 regions. They are called quadrants. Those quadrants will be numbered in counterclockwise manner. So the first one with positive x and y coordinates is called quadrant 1, and then quadrant 2, 3, and 4. Therefore, the angle, for example, 30 degrees is positioned in quadrant 1. Angle 120 degrees is positioned in quadrant 2, and so on. Remember that quadrants are actually regions of the plane without the boundary. If the terminal side of an angle is exactly on the x or y axis, for example, such angle, which is 90 degrees, is called quadrantal angle. Therefore, quadrantal angles are 0, 90, 180, 270, and so on, because we can actually rotate the angle more than 360. So another angle will be just 360. The following one, 360 plus 90, will be 450. So we'll have lots of such angles, either positive or negative. For example, negative 90, negative 180. There's infinitely many quadrantal angles. We'll see later on in trigonometry that it's important to know coterminal angles, because we'll learn in subsequent lessons that various trigonometric functions of coterminal angles will be actually the same. Therefore, we need to know the term coterminal angles. As the name indicates, those are angles that have the same terminal. That means, for example, here 60, and if we rotate the whole rotation and another 60, which is 420, these two angles are coterminal. They end up with the same terminal. Remember, angles in standard position always start from the positive x-axis, but it's important where they end. So we actually have infinitely many coterminal angles, because we could rotate once, we could rotate twice and then add 60. We could rotate any number of times around the circle and then add 360. So generally, an angle is coterminal to a given angle alpha if we can express this angle as alpha plus certain number of times of 360. So n is an integer. Could be alpha plus 1 times 360, 2 times 360, or could be minus 3 times 360, minus 5 times 360. It's infinitely many. Any integer produces another coterminal angle. We also need to learn how to change the decimal degrees into DMS mode, which is degrees, minutes, and seconds form. And for example, here we have first exercise to change 15.25 degrees into DMS mode. This ending is reasonably easy because it's like 0.25, which is like 1/4 of a whole degree. So we know that this is 15 degrees, and 1/4 of a degree on the side you can calculate 1/4 of 1 degree, but 1 degree is 60 minutes. So that's 15 minutes. So that wasn't too difficult. It's 15 degrees and 15 minutes. However, sometimes this ending could be a lot harder to do. So if you have your graphing calculator, you can take advantage of it and convert the decimal degree into degrees and seconds by using DMS mode. So maybe let's practice on 80.125 degrees to convert it into minutes and seconds. From the calculator, we'll end up with 80 degrees, 7 minutes, and 30 seconds. Okay, let's convert from DMS mode to the decimal degrees backwards. If we, for example, want to do it by hand without a calculator, I would say this is 65 degrees plus 30 minutes. What part of a degree is that? Well, it's 30 out of 60. That's already a fraction in degree mode. And plus 45 seconds. What part of a degree is that? Out of 3600. And then just add those fractions and we should end up with a nice decimal. The decimal here is 65.5125 degrees. So we can record this. So that's the way that you can deal with without a calculator. But if we have calculator, it's a good idea to know how to introduce this number to the calculator. I will show you in a second. So how do we introduce the degrees, minutes, and seconds? For example, 65 degrees. We use the angle feature. So second apps gives you angle. And here under 1 we have the degree sign. So enter. 65 degrees, 30 minutes, again second angle, under 2 it's minutes, and 45 seconds. Seconds can be obtained by this quotation mark, so alpha plus seconds, and enter. That converts to a decimal. And if we have a decimal, we can convert back to the degrees by using second apps, using angles. Under 4 we have DMS mode, so scroll to 4, enter, and yes, that goes back into degrees, minutes, and seconds. So that's how you can use your calculator to help yourself converting angles from one form to the other. And now try by yourself to convert this number 32 degrees, 10 minutes, and 12 seconds into the decimal degrees. You should end up with 32.17 degrees. For each angle, find a positive coterminal angle with measure less than 360, and then classify the angle by quadrant. So, the first angle is 560. I want to have a coterminal angle but less than 360. Since we know that coterminal angles are of this form, alpha, which is in our case 560, plus certain multiple of 360, could be negative multiple. So what we need to do is just subtract 360 from the angle that we have. That turned out to be 200. So the coterminal angle less than 360 is 200. And let's locate this in a system of coordinates. So 200 is more than 180 somewhere here. Therefore, this is in the third quadrant. Okay, therefore our answer is 200 in quadrant 3. Next we have 820. Okay, we can subtract 360, but then it's still too much. So let's subtract twice 360, which is 720. So we end up with 100. Our coterminal angle is 100 degrees, and it can be located in a system of coordinates more than 90, therefore in second quadrant, quadrant 2. And finally we have negative 75 degrees. You're welcome to try by yourself. What do we have to do? Well, let's add 360. If we do that, the resulting angle is 285. And how to locate it? Well, 285 is more than 270, so it's somewhere there. Therefore, we have fourth quadrant. 285 in a fourth quadrant. Aside of degrees, the other very popular type of measurement of an angle is a radian. Radian is a measure of a central angle subtended by an arc of length r on a circle of radius r. So, if I have a circle of radius r, and I open my angle in such a way that it will cut off the arc of the length equal to r, the same r as the radius here, then this angle has a measure of 1 radian, abbreviation RAD. So 1 radian is a lot larger angle than 1 degree. Notice what will happen if r is actually 1. What if our circle is a unit circle? Then the central angle theta of measure 1 radian is subtended by an arc of measure 1. So in a unit circle, a radian is such a central angle that it cuts off an arc of the length 1. Okay, from this definition, we can develop a relation between a central angle theta, the length of the arc, subtending it, and the radius of the circle. The central angle theta is the same as the length of the arc divided by the radius. Therefore, if the radius is 1, the central angle is exactly equal to the arc subtending it. And this is very useful because instead of talking about angles, we can talk about length of the arc in a unit circle. You can also look at this relation in the following way. The angle theta is directly proportional to the length of the arc subtending it. So in the unit circle, the angle is the same as the length of the arc, but if we, for example, double the radius, then the length of the subtending arc will also be doubled. So it's directly proportional to it. And the central angle theta is inversely proportional to the radius. That means if we, for example, keep the subtending arc the same, like this part is approximately the same as that part, then if the radius increases, like on my diagram is twice as large, therefore the angle decreases the same many times. So in this case, the angle is half of the previous one. Obviously, this formula could be remembered in a form theta times r equals s. Okay, so what's the radian measure of a complete revolution if we go around the whole circle? Well, let's think about unit circle. Since r is 1, then theta is exactly the same as s. But s really represents the circumference of the unit circle, which is 2 pi. Okay, therefore the theta that corresponds to the full revolution is actually equal to pi. Knowing that, we can easily answer the following questions. What is the radian measure of a straight angle on a straight line? Well, that's half of complete revolution, so it's just pi. Right angle, which is normally 90 degrees. Well, that means it's 1/4 of a complete revolution, or 1/2 of the straight, which is pi half. 45 degrees, oh, it's half of 90, so it's pi quarter. 30 degrees, oh, it's 1/3 of 90, so it's 1/3 of pi half, which is pi 6. And 60 degrees, that's 1/3 of 180 straight angle, which is pi divided by 3, pi thirds. So here we have a correspondence between degrees and radians. We need to fluently convert between special angles like listed here in degrees and in radians. And here are the conversion factors that could be useful for some other angles that are not so easily obtained as those above. So to convert from degrees to radians, we multiply by pi over 180. For example, if I have 10 degrees and I want to convert to radians, I want to get rid of degrees, therefore I use the conversion factor that will have degrees in the bottom and radians in the top in order to reduce degrees. The correspondence between degrees and radians is the easiest to remember by remembering pi is the same as 180. Pi radians is the same as 180 degrees. Therefore, I use pi in the top and 180 in the bottom. That's how we remember the conversion factor. So I'm not asking you to memorize those. I'm asking you to memorize just this and then use your common sense by placing the degrees in different level to cancel them, and then recover this conversion factor by relating pi and 180 in proper way. So we could simplify the 10 degrees with 10 degrees here, and we end up with pi 18ths radians. Similarly, to convert from radians to degrees, we multiply by the factor 180 over pi radians. Let's say I have 1/9 radian. Then it's enough to put radians in the bottom to cancel this radian and bring the degrees to the top. So again, pi radians corresponds to 180 degrees. Now we could reduce the radians and reduce the 9 with 180, leaving 20 here. And we get the final answer 20 over pi degrees. So the fact that we use pi in this number doesn't change the unit. It's still in degrees, even though the number could be ugly. Convert radians to degrees or degrees to radians. Give exact answer whenever possible, or round to 2 decimal places if you use calculator. And maybe I will convert these 3, for example, and you will try on your own the other 3. So 75 degrees. To convert to radians, I want to have degrees in the bottom and radians in the top. So 180 here, pi over there. I could reduce the degrees. I could reduce 75 and 180, for example, by 5. So in the bottom I will have 36. In the top I would have 15 pi. And 15 and 36 can be reduced once more by 3. So that becomes 5 pi over 12 radians. And the next example, this time we don't have the little circle in the top, so that's in radians. Notice that I tend to write radians in order for us not to get confused if the number is in radians or degrees. But the word radians doesn't even have to be written, and if it's a number without a degree, then we assume it's in radians. Therefore, if you really wish to express something in degrees, you must remember to write this degree sign. So in this case, 5 pi 6 is in radians. We want to convert into degrees, so radians will be reduced with the bottom and degrees in the top. 180 here, pi over there. Again, try to reduce, so we can cancel the pi, cancel the 6 with 180, that gives us 30 here, and 30 times 5 is 150 degrees. And one more example, 1.37. This time we should use calculator because this number is not very pleasant. So that's in radians. Again, the bottom will be pi radians and the top is 180 degrees. Multiply, divide by pi, and you should end up with approximately 78.5 degrees. So let's stop the video and try to convert these numbers to the other units, degrees to radians, radians to degrees, and I will give you the answer in a second. 420 degrees turn out to be 7 pi thirds. Negative 2 pi thirds radians is the same as negative 120 degrees. And finally, 156.71 degrees, it's approximately 2.74 radians. And here we have a wheel of correspondence between degree and radian measure of some angles. So those are the most often used angles like 0, 30, 45, 60, 90, and then corresponding angles in the other quadrants. So try to get familiar and more fluent in conversions between the degrees and radians. That will be very important for the future lessons. As we mentioned before, from the formula that theta is the same as the ratio of the arc length over the radius of the circle, we can convert this formula to S equals r times theta. So the length of the arc is radius times the angle. If radius is 1, then the length of the arc is the same as the angle. Also, we need to remember that this formula works only for thetas in radians. So the measurement must be in radians in order to use this formula. And let's do some application problems. Find the length of the arc S that subtends the central angle theta, which is 120 degrees, in a circle of radius equal to 20 centimeters. So we have a circle. The radius is 20 centimeters. The angle is 120, approximately this much. We need to find out the length of this arc S. Okay, so from the formula, S equals radius, which is 20 centimeters, times theta. But theta must be in radians, not in degrees. So I can multiply by 120 degrees, but then I have to convert it at once into radians. Okay, so we can divide by, for example, 10, and degrees are gone. We can also reduce by 6, so that's 3 and that's 2, which means that 120 degrees is like 2 pi thirds radians. If you remember that 60 degrees is pi thirds, then 120, which is twice as much, is 2 pi thirds. So we have 20 times 2 pi thirds. Therefore, it's the same as 40 pi thirds. That's the length of the arc, and it will be in centimeters. Obviously, if you wonder how much is that, you could plug it into the calculator and give the approximate value as well, but the exact value is usually more desirable. So the approximation is actually 41.9 centimeters. Now the second question, find the central angle subtended by the arc of length 5 centimeters in a circle of 4 centimeters in diameter. Okay, if my circle has 4 centimeters in diameter, therefore the radius of it is 2 centimeters. So we have r, we have the length is 5, we need the theta, so that's s. Therefore, from the formula, theta is the same as s over r. Therefore, it's the same as 5 over 2 radians. But what's 5 over 2? Maybe we would wish to have this answer in degrees. So in order to convert to degrees, we go 5, 2, radians in the bottom, so it's pi and 180 degrees. Now we can reduce the 2 with 180, leaving 90 here. So we end up with 5 times 90, 0.450 over pi degrees, which is approximately 143.2 degrees. That's the central angle subtended by the arc of length 5. Now let's find the number of radians in 2.5 revolutions. 2.5 revolutions is like 2.5 times 2 pi radians, because each revolution has 2 pi radians in it. Therefore, if we multiply, it's like 5 pi radians. And here's another application problem. A pulley with radius of 10 inches uses a belt to drive a pulley with a radius of 6 inches. We have two pulleys and the belt that connects them. Find the angle through which the smaller pulley turns as the 10-inch pulley makes one revolution. So the 10-inch goes around, and during that time, by what angle will the small pulley turn? Well, let's use the notation as on the diagram. For the large pulley, the angle could be called theta 1, and for the small, theta 2. Since when I look at the point on the belt, it doesn't matter if it moves around the big circle or the small circle, it will go through the same distance. So these two arcs, S1 and S2, will have to be exactly the same. We know that S1 must be equal to S2, but S1 is the same as the radius of the pulley, which is 10 times theta 1. However, S2 is the radius, which is 6 times theta 2. So that's the equation that we have. And now one complete rotation for the 10-inch pulley corresponds to angle 2 pi. Therefore, theta 1 is actually equal to 2 pi. So we have 10 times 2 pi equals 6 times theta 2, and it's easy to solve for theta 2. Therefore, theta 2 equals 20 pi divided by 6. So it could be simplified to 10 pi thirds. And you're welcome to use your calculator and convert this to degrees. That will turn out to be exactly 600 degrees. Okay, so one full revolution on a big circle corresponds to a little bit less than 2 revolutions of the small circle, because 2 revolutions would be 720 degrees. But this is 600, so it's more than 360, but less than 720. So it's 1 revolution and 240 degrees. Here we'll introduce an angular speed. Imagine that a point on the circle is moving. How fast is it moving in reference to the angle? That means how fast this angle is changing. That's what our interest is. So the angular speed of a moving point on a circular path with radius r at a constant rate of theta radians per unit of time is given by omega. Omega, it's a speed in terms of angle. Angle changes in certain units of time. So the ratio of the angle per time. It's a similar concept to the linear speed. For linear speed, we usually use the letter v, which is speed or velocity is distance over time. So in a circle situation, the distance covered by the point is the length of the arc in relation to the time passing. So linear speed is distance over time, and here for angular speed we have angle. This angle really corresponds to the distance. We've seen this before, that the angle theta, it's very strongly connected with the length of the arc. So in a way it has the nature of a distance. So again, angular speed is the ratio of the angle over time. Since s is the length of the arc subtending the central angle theta, then the linear speed of such point is given by the formula. As we said before, v is the length of the arc over time. However, the length of the arc is the same as r times theta, but theta over time can be replaced by the angular speed. Therefore, we end up with r times omega. So this gives us the relation between the linear and angular speed. The linear speed is directly proportional to the radius and directly proportional to the omega. The larger the circle, the point will have to go faster, and if the angle changes faster per unit of time, then the linear speed at the point is running faster as well. So v is directly proportional to the radius and to the angular speed. If each tire on a car has a radius of 30 centimeters and the tires are rotating 400 revolutions per minute, find the speed of the car in kilometers per hour. So let's picture out the situation. Let's say this is the road, here's a tire, the radius is 30 centimeters, and the tire is rolling on the road. Therefore, if I observe this point, it will go somehow like this, to the next point, to the next point, and so on. This circumference will actually be straightened up on the road. So if we mark this point on the tire by some sort of chalk, this point will leave marks every 2 pi r, every circumference. So this distance is really 2 pi r, and r is 30 centimeters. So this distance is in centimeters. Okay, what the question asks us to do, find the speed of the car in kilometers per hour. That means we need the linear speed, v. But v is the same as r times omega. R times omega. Well, we know r, however, the r is given in centimeters, and we need the final answer in kilometers per hour. So we need to convert 30 centimeters into kilometers. 30 centimeters times centimeters in the bottom, kilometers in the top. 1 kilometer corresponds to 10 to the 5 centimeters. What's our omega? Well, omega is connected with this piece of information. 400 revolutions per minute. So 400 times 2 pi gives me radians per minute. We need to convert revolutions into radians. But then the answer must be in hours, so another conversion, get rid of minutes, bring hours. 1 hour corresponds to 60 minutes. Okay, so it looks like we have everything what's needed. Therefore, we can just use a calculator, or we can try to simplify and do it a little bit in our heads. For example, there will be 1 0, 2, 3, 4 zeros. So you can get rid of 5, make it 1. So 3 times 4 times 2 times 6 will be 144 divided by 10. It's like 14.4 pi kilometers per hour. And we can use calculator to approximate this into 45.2 kilometers per hour. So that was the speed of the car. So you see on the diagram, this 2 pi times 30, we have 2 pi times 30, and this full revolution happens to repeat itself 400 times. So 400 of those segments during 1 minute. If we multiply 400 times 2 pi times 30 and then convert into proper units in kilometers per hour, then we have the answer. And the last problem, find the formula for the area of a sector of a circle with radius r and central angle theta. The sector of the circle with angle theta is this region cutted by the two rays that opens by angle theta. So how can we figure out the area of this region? We can look at the relation between area of the sector to the area of the whole circle. This relation should be the same as the length of this arc S to the circumference of the whole circle. So let A stands for area of the sector. Then we know that area of the sector over the area of the whole circle, which is pi r square, should be the same as the length of the arc, which is s, over 2 pi r. And now let's remember that s is the same as r times theta, so that could be written as r times theta over 2 pi r. So using this outside equation, we can reduce pi from both sides. We can reduce r within this fraction. Therefore, the rest of it, to solve for a, we have a equals multiplied by r squared to the other side. We'll have theta r squared over 2. So this will be the formula for area of a sector of a circle with given radius and angle theta. 1/2 of theta r squared. Well, let's think about it. Area is directly proportional to the angle. That makes sense because the larger the angle, the larger the area. And area has something to do with r squared. Well, area is always unit square, so that also makes sense. We also have a factor 1/2, which reminds me of area of a triangle. And as you see, this sector, well, it's very close to a triangle. The rest of it is accommodated by the angle theta. If we already have the formula of area of a sector of a circle in terms of given angle and radius, we can find the area of a sector of a circle with radius 10 and central angle 2 pi fifth. So just plug it into the formula. Area is, remember, theta is always in radians, and yes, we have this in radians, so that's great. 2 pi fifth times radius, 10 centimeters, so 10 squared, and divide by 2, so 1/2 of it times 1/2. Okay, we can reduce the 2, and here we have 100 over 5, which is the same as 20 pi centimeters square, because its area, it's a unit square, and the units are centimeters. So 20 pi centimeters square. Final answer.